Hello everyone. Today I will introduce this paper created a way to recognize characters to text. It's called an end-to-end trainable neural network for image-based sequence recognition and its application to scene text recognition. It uses a structure we call CRNN. I will talk about the structure of CRNN. Basically it's a CNN plus RNN, but it's a special design of CNN, so it can change a line of picture into sequential signals, so you can connect it with RNN. And after that, I will talk about the a technique called CTC. That is how you when you get the result of RNN, how can you put it into text? And then I will go through the code so we can go a little bit deeper to the structure of CRNN. Firstly, I'd like to give a big structure. What is this CRNN looks like? Here is input image. And here is the input image, and by CNN, we give it convolutional features. So basically, this image gets mapped to different, we can think this as a channel. Each channel is a result of convolutional kernel. So different signals are passing through. And then this green part represents the result of CNN. You can see this is a sequential signal. Each bar is a position mapped to a position of x axle. And this length, we can think this as the length of the feature. Then we connect this part to RNN, and then this part is CTC. And can use LSTM or GRU. We can have several different form of RNN that we can select. And after this after RNN, we can think this as at each position we have different class, and each one have a possibility. For example, if we design this task for recognize English lowercase, so this will be 26 different classes, and each position will have a possibility. I will introduce the concept of CTC, which is a connectionist temporal classification. The idea of CTC actually emerged in the field of recognize voice into text, and the idea comes from this. There will be a lot of align labels if we want to label each window of voice sample or image sample. It's a similar question for CTC. For example, if we cut this image into every 4 pixels or every 8 pixels, people will have to label, maybe the first label of the first window will be blank, and this one is a S, and this one is a S, this one is a S, and this part may be a T. So there will be a lot of human labels, which is much difficult than just label this picture as a state. So the question is there a better, easier way so we can label a image or a voice sample? The answer is yes. And first we will introduce a special character. We can name this as a CTC blank, which basically means it's we label this as a change of a classification. So when we decipher a CTC code, the first thing is we merge repeat characters. So if we get a CTC code like this, first position H, second position H, third position E, CTC blank, L, 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 CTC blank, L, L, O. First step, we merge same characters. So then we get this HE, CC blank, L, CC blank, L, O. And then we remove all the CC blank tokens. Then we get this HELLO, which is hello. So this is one path of CTC. Position 1, X2 is position 2, position 3, position 4. So each of these points, you can think this as at position 1, we have different class we can go to. But think this as each class has a different possibility. We are thinking this as each from position 1 to position 2, we have many different paths. So let's say the possibility of get the label L with possibility of label L in the condition that we have this possibility matrix. So Y is a possibility matrix. We get this possibility matrix from either image or voice sample. And we give the sample to the CRNN. For example, in the image scenario, we give this image to CRNN. The output of CTC is the output of the RNN. So output of this RNN is at each position we have 27 classification, and each one have a possibility. So the whole possibility of given this Y matrix, and we get the label L, is a summation of a certain path. So pi means certain path. For example, from here to here to here to here to here to here is a path, and we have other paths. So all the paths give the result of, for example, hello. So we want to know, given this matrix, how much possibility we can get hello, which is a summation of all the paths we can get hello. because different paths may get into same final label. From the example we got here, this is one path. But if we change some of the label here, for example, if we change the second label from H to E, we still get hello. We get the hello from the given matrix. We need to sum all the possible paths. This is a basic idea of CTC. Detail of their CRNN model structures. So here is the W means the width of the width of image. So for the paper, 32 means the height of a pixel, and they use a grayscale image, which means they only have one channel there. And for convolution, maps 64 means the first layer of convolution, they have 64 kernels. And the K means kernel size. So we have 64 kernels. Each kernel is 3 by 3. And S means a stride. It means basically means you have a 3 times 3 kernel, and each time you move 1 pixel. Each time you move 1 pixel to scan it. And P means padding. So you want to padding at the front and at the end. So this is a convolution. For max, and after convolution, you have a max pooling, and then convolution, then max pooling. And we will talk about the how the size change through convolution and max pooling later. And after that, we have a bidirectional LSTM, and the hidden unit is 256. So here is the structure, how you create this structure in the code. So basically it means kernel size 3. The last layer is special. Last layer kernel size is 2, and the padding is 1. The last layer is 0, and the stride at each layer is 3. And this is how many kernels you have for each layer. And I want to talk about this equation. This equation means how the weight or how the height change after one layer, either pooling or convolution. For example, we have the last layer as a width W, because we are padding at the front and the end. So you need to plus 2 times P. Then you want to minus K. K means the kernel size. So most of the kernel size is 3. The last one is 2. And then you want to divide it by the stride. So for most of the convolution, it's 1. So you can see this special design. After this special design, the result is each after the convolutional layer, the size is still the same. So this is how they design these numbers. They want to keep keep the width and height the same after convolutional layer. Here is their code. If you go to the GitHub and go to the models, they have a file called crnn.py, and this is their crnn part. And so this part, they just this function is how you build a convolutional layer. And after that, they add a max pooling here, and the parameter is 2 and 2. The first 2 means the window size, and the second 2 means the stride. If we go back to the equation, if we put here, the padding is 0. The last parameter is padding. The padding is 0. The kernel size is 2, so minus 2. Then divided by 2. Then we have W divided by 2 minus 1. Then we plus 1. So basically, this pooling layer means we decrease the width and height by half. And then they design a special max pooling 222101, which means for kernel size y and x the same, 2 by 2 window. And but for stride, this is different. For the y direction, stride is 2. For x direction, stride is 1. And for padding, y is 0, and for padding, x is 1. If we 256 because of this, and the height become 4, and the width is 33. We have this special layer of the last convolutional layer, and for the stride is 1, but kernel size is 2, and the padding is 0. So let's look at the for example, we have the height as 2, and because padding is 0, we plus 0, and we minus 2, and the stride is 1 divided by 1 and plus 1 divided by 1 plus 1. So we have the height become 1, and the width is 34. Actually 34, and padding is 0, so we minus 2, and stride is 1, so you get 32. Still plus 1, it's 33. So the last result is you have 33 positions, and each position you have a 512 dimension feature. So this is the structure of this CRNN model. I hope this can be helpful. Thank you.